Hi, in this video we are going to talk about steady state mixed flow reactor. So to obtain the performance equation for a steady state mixed flow reactor, we are going to first write down the material balance for the reactor. So we know that input equals to output plus disappearance of reactant plus accumulation. Now we have a steady state process. So this accumulation term is equivalent to 0. Okay. And one thing to remember about a mixed flow reactor is that the composition is uniform throughout the reactor. So there is no differential volume that you need to consider when you are establishing the material balance. Okay. So first let me just draw a schematic of how a mixed flow reactor would look like. So it is also a reaction vessel where you have one input stream and the reaction mixture is here. Generally there is a stirrer and there is an outlet stream. So on the inlet you have a composition Ca0, a molar flow rate Fa0, a volumetric feed rate V naught, and the conversion of the element, or rather I should say the reactant A, is 0. But at the outlet, let's say the final concentration of ABCA, the final conversion be XA, VF is the final volumetric feed flow rate, output flow rate, and FA is the final output molar flow rate. Now we are going to write the model, like the model equation itself. That's what I mean. So if you like consider the balance with respect to the component A, then on the input side you have Fa0, on the output you have Fa0 1 minus Xa. This is how much has converted. Plus there is a disappearance with respect to time, so minus Ra multiplied by V. V is the total volume of the reactor. I should write it over here. V is the total volume of the reactor, and we do not have an accumulation term. So once you just break down these equations, you will get Fa0 Xa equals to minus Ra multiplied by V. Okay. Now if you rearrange this, then you can write V by Fa0 equals to Xa by minus Ra, and this V by Fa0 can be written as tau by Ca0. Tau, if you remember, is the space time, and this again can be written as del Xa divided by minus Ra. Now you know tau is 1 by space velocity, that is 1 by s, which is equals to V by V naught. So you can also write V Ca0 by Fa0 equals to Ca0 Xa divided by minus Ra. Okay, and this is valid for any volume ratio epsilon A. Okay, and the measures for Xa and minus Ra are done at exit stream conditions. Okay, exit stream conditions means the outlet stream. Since the composition is uniform throughout, so the exit stream condition is considered the same as within the reactor. Okay, now if like you are talking about a general case that the feed is based on some conversion and it enters the reactor in a partially converted form and then leaves at some finally converted form, then how would you write it? Okay, so let's write that expression, that is something like v by fa0 equals to delta xa by minus ra, which we wrote earlier, and this delta xa can be written as xaf minus xai divided by minus ra at final conditions. Okay, like I said, the exit stream conditions are important. Xai is the conversion of the partially converted feed and XAF is the final conversion at the output stream. Now, if you have a constant density system, okay, a special case is when you have a constant density system, that is for most of the liquid phase reactions and some gas phase reactions. So in that case you can relate xa equals to 1 minus ca by ca naught, right? This is already known to us. So you can directly write the performance equation in terms of concentration. This you can do only if you have a constant density system. But if you do not have a constant density system, then you must refer to the general equations written in terms of the molar feed rate. By constant density system, I mean epsilon A equals to 0. Okay. So, if you write down the performance equations now, V by Fa0 equals to Xa by minus Ra equals to Ca0 minus Ca divided by Ca0 multiplied by minus Ra, right? And if you write in terms of the space time, tau equals to V by final volumetric rate equals to Ca0 Xa by minus Ra, which again is equals to Ca0 minus Ca by minus Ra. Okay, now these expressions are simply relating these terms xa, then there is fa0, v and minus ra, like I said. So if you know any three of the above, you can find the fourth one. So in most cases where you are designing a reactor, the size of the reactor is required for a given conversion from the reactor. Okay, and in kinetic studies, each steady state run gives the reaction rate for the conditions within the reactor. The ease with which you interpret the data from a mixed flow reactor is what is the most attractive feature about studying these kind of reactors. It makes it very easy for experimental studies related to kinetics, especially in case of multiple reactions. Okay, now I'm going to just graphically show to you what the design equation is actually representing. So if you plot a graph and on the x-axis you have the conversion and on the y-axis you have the reciprocal of rate, then you will get a curve like this, and the area within this rectangular area, let me just cross the rectangular area. The area within this rectangular shape is going to give us V by Fa0 or tau by Ca0. Okay, this is for the general case, that is any epsilon A. But if you have if you know for certain that epsilon A is equals to 0, that is for a constant density system, then you can directly plot with respect to concentration. So on x-axis you plot Ca, and on y-axis you have the reciprocal of rate equation. Sorry, I shouldn't write minus over here. Yeah, so reciprocal of the rate, then you get a curve like this. So the area within the rectangle is going to denote tau, that is V multiplied by Ca0 divided by Fa0. This is the graphical representation of the design equations for a mixed flow reactor. Now, to better solidify our understanding, let us just take a small numerical example, and I am taking this from one of the example problems of Levenspiel book. You can go back to the book and you can go through the other examples given there. So let's say you have an elementary liquid phase reaction, okay, which is like A plus 2B reversibly gives R, okay, and the rate equation is given as this: minus RA equals to minus half RV, which is equals to 12.5 liter square per mole square minute multiplied by CA/CB square minus 1.5 minute inverse multiplied by CR, and the whole unit of this is mole per liter minute. Okay, this is the rate equation, and this reaction is taking place in a volume of 6 liter steady state mixed flow reactor. So far so good. Now let me draw a schematic to help us with the problem understanding. So we have a vessel and we know the reaction that is occurring, and the volume V is 6 liters, and there is a stirrer over here. Now in the input stream we have two streams. One is of A, where initial concentration of A is 1.4 moles per liter, and we have another stream B, where the initial concentration is 0.8 moles per liter. Okay, and they are in equal volumetric flow rates. Okay, so they have equal volumetric flow rates, meaning VA, small va equals to small vb equals to V. Okay, equal volumetric flow rate at inlet. Okay, now at the output it has been told that 75% conversion of B is seen. Okay, so the outlet condition is that 75% conversion of B has been achieved. What should be the flow rate of each stream? That is what we need to find out. And they have also mentioned that you have to assume that this is a constant density system, that is epsilon A equals to 0. Okay, so how do we solve this problem? I hope the problem statement is clear. Simply, we have a liquid phase reaction, a reversible reaction, and the rate equation has been given to us. We are told that we have a steady state mixed flow reactor of 6 liter volume, and the input or inlet point has two flow rates, equal volumetric flow rates, and the concentrations of the streams are specified. At the outlet, we have 75% conversion of the second reactant B, okay, which also in this case is the limiting reactant. Okay, so if B is finished, the reaction is over. So 75% conversion of B is seen. Then what will be the flow rate of each of these streams if we assume that this is a constant density system? Okay, so now let us go about solving this. So let us just once again reiterate the information we have. We know Ca0 equals to 1.4 moles per liter and Cb0 is zero point 0.8 moles per liter. We do not have any product R in the input stream, so that is 0. Cr0 equals to 0. Okay, so from the number, one thing we are clear about is that if B is over, then the reaction will not progress anymore. Okay, now we are aware of one thing, that is B is consumed up to 75% conversion, right? So if B is achieving 75% conversion, then you can simply say Cb equals to 0.8 minus 0.75 of zero point 0.8 moles per liter. This is pretty simple. So you will get something 0.8 minus 0.6, which is equivalent to 0.2 moles per liter. This is Cb. Now we know 0.6 moles of B is reacting. Now we'll go back to the reaction stoichiometry. So for 1 mole of A, 2 moles of B will be reacting, right? So now coming down, let us find what will Ca be. So Ca equals to 1.4 minus zero point 0.6 by 2. From the reaction stoichiometry you get this. So 0.6 moles of B are being converted. With respect to that, how many moles of A has been reacted per liter? That is what we are finding. So we get 1.1 mole per liter, right? Accordingly, we can say Cr equals to, let's see again. So 2B will give you 1 R, right? Therefore, R equals to 0.6 by 2, that is 0.3 moles per liter. So far so good. Now we are going to write the rate and the rate equation that we have been given, and we are going to solve the entire problem in terms of b. Okay, so if you write the rate equation in terms of the component b, minus rb equals to 2 multiplied by minus ra, because we had minus ra equals to minus half of rb, right? Now if you plug in the values, this becomes 2 multiplied by 12.5 CACB square minus 2 into 1.5 CR. Okay, and if you write all the values over here, then you will get zero point 0.2 mole per liter minute as your minus RB. Okay, so the rate in terms of component B is now found. Now if there is no density change, okay, if epsilon equals to 0, okay, with respect to the limiting reactant, then we can write tau equals to V by small v, and this again becomes equals to CB0 minus CB by minus RB. We have just studied this relationship for constant density systems. Now all we have to do is solve for small v. Okay, so small v now becomes the subject of equation as capital V, which is the volume, multiplied by minus RB divided by CB0 minus CB. Now if you just plug in the value, so V was 6 liters minus RB is 0 0.2 moles per liter minute divided by 0.8 minus 0.6. Okay, CB0 was 0.8, final CB was 0.6. So you will get 6 liters per minute. So the volumetric feed rate for the entire system becomes 6 liters per minute. Now since we have two feed streams, so we have two feed streams, therefore 3 liters per minute of each of the two streams. This becomes the design for our reactor. This is one of the design problems that I have taken up. There are other types of problems also available in the book and in the exercise of the book, which you can solve for your reference. The idea is that depending on the type of system you have, whether it's a constant density system or a general case, you should apply the correct performance equations. My personal advice is to keep in mind the general case equations for sure. In case you have forgotten it, you can always use the material balance to just deduce the equation. That is it. Thank you.